Well, hello, calculus fans. So today we're going to take a look at the definition of the definite integral. So the idea here is we'll see what all this business with Riemann sums and rectangular approximations has been leading up to. And in our next section, learn about a more efficient way to evaluate the results of taking limits of these Riemann sums. Many problems in science and engineering can be solved by the following technique. The problem can be cut into pieces, small pieces. The answer to each of these small problems can be approximated, and then those answers are added together to get an approximation to the answer to the original problem. You'll see many examples of this next semester in Math 166, and we're already seeing examples of that this semester in our calculation of area by cutting it up into rectangles and our calculation of distance traveled and displacement found by cutting the time interval up into small pieces. So one example, of course, as mentioned, is the calculation of area under the graph. We've seen several examples of this sort of thing. And here's the kind of figure we see when we do this. We partition part of the x-axis that spans the area into intervals, and then use these intervals as the basis of rectangles. We determine the heights of these rectangles by finding a point in each interval. For example, this point in the first interval, we would be labeling C1 before. Looks like C2 is right here at the right endpoint of the second interval, and so forth. But we use the heights, or these representative points, and then the heights to the curve, that is the function value, to determine the height of the rectangle. So the heights here run something like this. Okay. So we've done a few of these calculations before. Here's another example. Suppose we know the velocity of an object. It's moving in a horizontal line, and its velocity is v of t at time t. We can use the Riemann sum idea to calculate the change in position or displacement of the object from some time a to some time b. Now, if we graph the velocity function, we see that this problem actually looks a lot like the area problem. So here's our graph of the velocity function. Now we have some times here when the velocity is negative. And of course, we know in those interpretations that tells us what direction the object's moving. If positive velocity means motion to the right, then negative velocity means motion to the left. And so this object is going to travel backwards or to the left for a while, and then once time reaches this point, turn around and start heading to the right. So we can use a rectangle type approach to figure out what the displacement is, or to approximate it as follows. Here we've more or less filled the area between the graph and the t-axis with rectangles. Now in this case, the horizontal axis is in time, perhaps in seconds, as we see here. And the vertical axis is a velocity, so perhaps that's in meters per second. So this first rectangle down here, which is below the axis, we see that the v value at the point C1, which is where that dotted line is negative, and the length of that interval, we'll call it delta t, represents a small time, delta t1, and this result will come out to be negative, and that tells us the motion, the object moved to the left a short distance. And so if perhaps here's our axis, and the object started here, this first calculation would say, okay, looks like we've moved a little bit to the left there. The second rectangle also is below the axis, so it'll contribute a negative, and so that'll be a little bit more motion to the left, maybe slightly more because it looks like this rectangle has a larger area than the first one. And then we have more motion to the left, and then a little more motion to the left from that small rectangle there. And then from that point on, our approximations or our rectangles are above the axis, and so then the object starts moving the other way. And if, let's say, by the time we hit time B, we're at this point, we then have this displacement. So adding these rectangles, thinking of the ones below the axis negative, or distance to the left, or negative distance, and the ones above as positive. When we add these rectangles, we get the so-called displacement. That is, how far is the object from its starting position. Now, also in a lot of these problems, units are important. So often we want to pay attention to the units on the horizontal and vertical axis. In this case, the horizontal axis had units of time or seconds, and the vertical axis had units of meters per second. So when we do one of these multiplications, we're multiplying meters per second times second, and so we see we are getting distance in meters. So the units help us interpret the meaning of the calculation. Now, as we've seen in sections 5.1 and 5.2, often these approximations with a few rectangles, such as this one, if we're trying to calculate the area under the curve, that's not very satisfying. We see there's a lot of error. The white space between the graphs and the rectangles is undercount, but sometimes the rectangles are too big and they slop over the top of the region, so there's overcount. So rectangles like this may give us a rough approximation of the area under the graph, but perhaps not as good as we'd like. On the other hand, here's a picture of what we'd get if we took 100 rectangles. We took them to be of equal width, and here we can see those 100 rectangles conform very nicely to the graph of the curve, and if we added the area of these rectangles, we'd be much more confident that we'd have the area under the graph. The velocity problem is similar. Again, we get a rough approximation to the displacement from this picture, but down here with again 100 rectangles, again of equal width in this case, things look a lot better. We get the negative travel down here, and it looks like we're conforming to the curve pretty well. So if I add the quote areas of all these rectangles, each of which has units of meters, we would get the travel to the left, and then this calculation with these rectangles would give us the travel to the right, and so perhaps a better idea of what the displacement is. So there are reasons for taking more and more rectangles, though that can be a lot of work, but the definition of the definite integral and the work we do later on will help us make that work quite a bit easier. So here's the definition of the definite integral, pretty much as it's stated in your book. So we're going to assume we have a function defined on some interval, say from a to b, and we'll consider the Riemann sums we can form. So there's a lot of knowledge behind this sum. We have to know what the CKs mean, etc. We'll review that in just a moment. But there is a Riemann sum. The summation as k runs from 1 to infinity, f of ck times delta xk. This is associated with a partition, p, x1, x2, xn. So those are the points we use to carve up the interval. And then we have a choice of representative points, one in each interval, C1 in the first interval, C2 in the second interval, and so forth, and Cn in the last or the nth interval. Now, we look at all these Riemann sums we can form, and we're interested in what happens to those as we take more and more rectangles that are thinner and thinner. In other words, as we let the mesh of the partition approach zero. And if these numbers, these Riemann sum numbers we get, all approach some particular number j, we call that number the definite integral of f on the interval from a to b. We use the integral notation, which we see down here, to denote this value or this limit. And so here in summary is what our limit looks like. There's the Riemann sum. We want to see what happens as we let the mesh of the partition go to zero. Again, that means the rectangles are getting thinner. In fact, the width of all the rectangles is going to zero. And so, of course, as a result, we're also approaching infinitely many rectangles. Because if we use a lot of skinny rectangles, we need a lot of them to fill in under the area. So we're going to do a little work with this definition to kind of get used to seeing what it looks like. So again, the fact the mesh goes to zero, remember what mesh means. It's the mesh of a partition is the length of the longest little subinterval. The mesh goes to zero means that we are letting the rectangles get very, very thin. In fact, the widths are approaching zero, And of course, that means the numbers of rectangles is very large and approaches infinity in the limit. Now keep in mind that the definite integral is a number. So each Riemann sum is a number. It's a sum of areas of rectangles or a sum of little distances traveled. The limit of these numbers, that is the number that these are all getting close to, is the definite integral, and that limit itself is a number. So although this notation may look kind of daunting at first, when we work it out, it always comes out to be some real number. So here's a picture kind of reminding us what was behind these Riemann sums. So with every Riemann sum, you have to have a partition. So here we have a partition with 9 points, x0 to x8. The x0 is always the left point of the interval, the A in this case, and the x8, the last point of the partition, is the right endpoint of our interval, which in this case is B. So here we've mapped out possible x1, x2, etc. through x8. And then, of course, if we want to think about the area interpretation here, we have to find the heights of these rectangles. And we do those heights by just moving from the x-axis to the graph. So here we just pick a point in each interval, a C1 in the first interval, C2 in the second, C3 in the third, etc. And finally, C sub 8 in the eighth interval. Now, I know many of you have told me that in high school you only work with left endpoints or right endpoints, and for the most part that's good enough. But really, when we define this definite integral, we have to understand that these special points can be picked anywhere in each of the small intervals. Again, normally when we want to work with this sum, we'll pick something consistent like always left endpoints or always right endpoints just to make the calculations easier. Now finally, we have these delta x sub k's out here, and these delta x sub k's denote, again, those might be different if we're using kind of a uneven partition. And so delta x1 is just x1 minus x0, and that gives us the width of that first interval, just the length of that first interval up there. Delta x2, x2 minus x1 gives us the width of this next interval, or the width of the second rectangle, and so forth. So anytime you see the definite integral sign or a Riemann sum, you have to remember that the Riemann sum is behind the definite integral, and behind the Riemann sum is all this business about partitions, special points, what the delta xk's are, etc. You can't really understand what this sum is telling you in a vacuum unless you know all this background about partition points and special points and so forth. So as we'll see in future weeks, the definite integral can be used to solve many problems, and this means that the definite integral can mean many, many things or be interpreted in many ways. Often it'll just depend on the context of the problem you're trying to solve. But nonetheless, no matter how much you learn about definite integrals, one of the most useful and visual ways is the area interpretation. So we're going to do a lot of work with that this semester and next, but we're going to kind of rest on the following fact, that if f of x is non-negative on an interval AB, then the integral from a to b f of x dx is equal to the area under the graph and above the x-axis for this interval. Now we will later on in the next couple weeks use integrals to find areas between and under curves, but this interpretation says we can also use the area interpretation to evaluate some integrals. Here's an example. Let's evaluate the integral from -1 to 4 of 2x plus 3 dx. So rather than go through the Riemann sums and the limits, I can now think of the problem this way. I know that because this function stays above the x-axis on the interval from -1 to 4, in fact, we've graphed it over here to show this. So there's the interval -1 to 4, which is the interval of integration here. And here's the graph of y equals 2x plus 3. And the integral is just this area under the graph. Now, if you take a normal complicated function, that area could be rather complicated, but in this case, that area is just a trapezoid. And we have formulas for areas of trapezoids, so we can compute that area just by geometry. That area turns out to be the following. So this trapezoid has parallel sides of 1 and 4 and 11 rather. Remember, trapezoid is just a quadrilateral with two parallel sides. The height of this trapezoid is 5. The height is lying horizontally here, but it's the perpendicular distance between the two vertical sides. So the area of a trapezoid is found by taking the average of the lengths of those two parallel sides, in this case 1 plus 11 over 2, and multiplying by the height, and that calculation gives 30. And so we have now actually evaluated this integral. The integral from -1 to 4, 2x plus 3 dx is equal to 30. This error interpretation can also be used even when the function takes on negative values. In this case, we usually interpret contributions to regions below the axis as negative areas, and then we add the negative and positive areas together, in effect subtracting the negative areas from the positive. So probably best to see this with an example. Let's evaluate the integral from 0 to 2 pi of sine of theta d theta. So once again, we're going to appeal to areas to solve this. So we graph the function. So here's the graph of y equals sine theta on the interval from 0 to 2 pi, and actually a little bit more. And so we're going from here to here. And if we use our interpretation of areas below the axis being negative, we can observe the following. So these two regions under the graph, these parts of the curve, these are congruent. In other words, they have the same shape and same area, etc. So whatever area A is up here is going to be the same as the area A down here. But of course, this area, the one down here, contributes a negative. So we can evaluate this integral by saying, well, this integral gives us a positive area A here, and then for the part below the axis, we interpret that as negative A area, and so the result turns out to be 0. And indeed, this is correct. The integral from 0 to 2 pi of sine theta d theta does turn out to be 0. We'll see that also in the next section when we talk about the fundamental theorem of calculus. Like derivatives and antiderivatives, the definite integral follows many rules. In fact, there's a few more of them here because they also affect, or we also have to say something about the particular limits on the integral. So these are the rules of the definite integration, the rules followed by definite integrals. They're on page 317 of your textbook. So you really have to know these. We're not going to spend too much time with them, but let's take a look at a few of them very quickly. This first one, notice to say this is a definition, so we're just going to take this as a definition. And this just says that if you have an integral from a to b, like we have here, and you reverse the order of the limits on the integral, then you negate the integral. Okay. So the integral from b to a of f of x dx is minus the integral from a to b f of x dx. Another definition tells us the integral from a to a fx dx is 0. This kind of makes sense because if you think of integrals as representing areas, we are here looking at the area just under the graph from a to a. That'd be the area of a line, and of course that turns out to be 0. We have the linearity rules. Constant multiples can factor in front of definite integrals. So if I have a number k like a 2 or a 3 here, I bring it out in front of the integral and then focus on evaluating the integral. Likewise, integrals can be split up along plus and minus signs. So if I know the integral of f and I know the integral of g, then I know the integral of f plus g or f minus g. This fifth one is a little different, but again, it's really saying something pretty obvious about areas. Let's suppose we have a graph here, and we are integrating from a to c. This is the integral we see on the right over here, and then there's a b in the middle here. So the integral from a to c, we can think of as the area of this whole region under the graph between a and c. The integral from a to b gives us this piece on the left, and the integral from b to c gives us this piece on the right. So if we think of this in terms of areas, it just says the big area is the sum of the two little areas. And then a couple inequalities that are interesting. I'll let you read those in your book, and you'll do some exercise with those in the My Math Lab homework. But the inequalities are important because it's often desirable to know when one integral is bigger than another, when one area is bigger than another, when one object has traveled further than another, and these inequalities can help you wrestle with notions like that. So let's take a look at one example of applying these principles. So in this case, we're given the values of four integrals. The integral of f of x from 3 to 8 is 4. The integral of g of x from 3 to 8 dx is minus 1. Then we have the integral of f from 3 to 5 is 2, and the integral of g from 3 to 5 is minus 7. So we're asked then to find the value of the integral from 5 to 8 of twice f of x minus 5g of x dx. So we're going to do this by just applying several of the rules we saw on the previous page. We first will apply the sum difference rule. So we have a difference of two integrals, and we can, as we saw, split the integral up along the minus sign. And then the constant multiple rule says we can bring the 2 out in front of the first of those integrals and the 5 out in front of the second. And so now we can focus on these integrals of f and g without the constants in front. Now for these, we're going to go to rule number 5, which was that one about adding areas. We'll just focus on this one. The one on the right here is very similar. Over here, we saw in rule 4 the integral from 3 to 5, or 3 to 8 rather, of f of x dx is equal to the integral from 3 to 5 of f of x dx, and then plus the integral from 5 to 8 of f of x dx. Now, we have the integral from 5 to 8, and so evidently we can express that as the difference of the integral from 3 to 8 and the integral from 3 to 5. And so that's what happened up here. And then we handled the g integral in a similar way. And of course we did this because these integrals from 3 to 8 and 3 to 5, the values of those integrals are given up here. So we're at the point now where it's just a matter of substituting in the numbers. And when we do that, we find our integral can be expressed as 2 times this value, which was 4, minus the 3 to 5 integral of f, which was 2. So there's the 4 minus the 2. And then likewise the minus 1 minus minus 7 for a value of minus 26. So please look over these rules on in your book, practice with some of the inequalities, read over the justification for these, and work some problems. So I think you'll find this is a kind of a satisfying thing to work on, especially it's going to lead us from all the bother and work behind working with the Riemann sums by the time we get through the next chapter. Good night.